In this video, we will look at the big omega notation. In the analysis of algorithms, we focus on the number of times the operations are performed by an algorithm using the step count method. The step count method considers the frequency or the total number of times each statement is executed, and by adding the frequency of each step, the step count of the entire algorithm is computed. Now, mathematically, the number of operations needed to execute an algorithm is represented as a runtime function f of n, where n is the size of the input. Let us graphically plot the function f of n. So, we will have n, which is the input size on the x-axis, and the running time on the y-axis. So, graphically, when the function f of n is plotted, it will look like this, where as the input size n increases, the running time increases. Then the question is, what is the lower bound for this function? Let us consider another function g of n in such a way that c multiplied by the function g of n is less than the function f of n. If you observe the function g of n is lesser than the function f of n after some value or input n0. Now, mathematically, we can write this as f of n greater than equal to c multiplied by g of n for n greater than n0. Here in this equation, c is a constant and is greater than 0 and n0 is greater than equal to 1. Now, if we are able to satisfy this equation, then we can say that f of n is big omega of g of n. And this definition is known as big omega notation. The big omega notation is used to describe the lower bound of an algorithm. Therefore, asymptotically, the function g of n is lower bound for the function f of n. Now let us take an example to prove this notation. Let us consider that we have a function f of n as 5n plus 4 and another function g of n as n. Then, by the big omega definition, we need to find a constant c greater than 0 and an integer n such that f of n is more than c g of n. That is, in this case, 5n plus 4 greater than equal to c multiplied by n for every integer n greater than equal to n0. Now, since n is greater than equal to n0 and n0 must be greater than equal to 1, therefore, n must be greater than equal to 1. By looking at the expression, we can consider the possible choice of c as 1 and n as 1. So, when we evaluate this expression, 5n plus 4 greater than equal to cn, using c as 1 and n as 1, we get 5 multiplied by n, which is 1, plus 4 greater than equal to c, which is 1, multiplied by n, which is 1. So, we have 5 multiplied by 1, which is 5, plus 4, which is 9, greater than equal to 1 multiplied by 1, which is 1. So, we have 9 greater than equal to 1, which satisfies this expression. Indeed, this is one of the infinitely many choices available for the value of c and n. So, we can say that the function f of n, that is 5n plus 4, is big omega of g of n. And since g of n is n, hence we say that f of n is equivalent to big omega of n. The big omega notation allows us to say that a function f of n is greater than or equal to another function g of n up to a constant c, and in the asymptotic way as n grows towards infinity.